Welcome to qnawire.
Welcome to a new problem, this time involving a physics professor being pushed up a ramp. So we have a physics professor is sitting on a chair, and they're being pushed up a ramp. So initially, the professor was at the base of the ramp. We have a bunch of students that's pushing the professor with a horizontal force. So the force is horizontal that way. And there are a couple of things that are going to happen. First of all, the professor has a weight, mg, and the weight has two components. One is towards the um, vertical, it's perpendicular to the plane of the incline, and then the other one is mg sine theta, which is horizontal to the plane of the incline. Remember, the students are pushing the professor this way, and so the force they're exerting on the professor has also two components. There is one that's going that way that happens to be F cosine of theta. Remember, this is F, and so there's a force F cosine of theta, and we can see there's a resultant force on the professor that's causing the professor to move upwards. So that's the scenario we have. We're going to use the work energy theorem in this problem. So we need to use the work energy theorem. Okay, work energy theorem, and the purpose for that is to say the total work done on the professor, total work on professor is equivalent to the change in kinetic energy as they're pushing the professor upwards. There are just certain numbers we need. Theta happens to be 30 degrees. That's the slope of the incline. The other thing is that the professor is being pushed a distance of from right here up until there, it's 2.8 meters. That's the distance they're pushing the professor along the incline with a constant force. This force is given as 600 newtons. So that's what's happening. The initial velocity of the professor at the bottom of the ramp, that's like right here. Okay, the initial velocity of the professor happens to be, I'm just going to call it v initial, is given by 2.00 meters per second. And the weight or the mass of the professor plus the chair, so we'll call that this is m, is a mass of the professor, plus the chair they're sitting on. It's an irony. You could think of the professor as the chair of the department, but the professor is sitting on the chair. So the mass is given as 85.0 kilograms. The purpose of the problem is we want to find the speed, the final speed of the professor at the top of the ramp. So V final, that's our goal. So the total work on the professor has to do with the resultant force on the professor. So F cosine theta minus mg sine theta times the displacement of the professor, which happens to be, now I'm going to use D instead of S. Sometimes you confuse S with other numbers. So I'll just use D as the displacement. And it's given right here. So D happens to be 2.8, so we want to be sure about that. That's the total work on the professor, and it's equivalent to 1/2 mv final squared minus 1/2 mv initial squared. We don't know what mv final squared, and that's what we're trying to get. So this becomes F cosine of theta minus mg sine theta times d, and then plus 1/2 mv initial squared equals to 1/2 mv final squared. So that's where we are right now. Our target is this mv final squared, and keeping up with the trends that we've had before, where we focus more on shifting the variables up until the end before solving the problem. So we want to get rid of the fraction. So this is 2, and then this is 2, and then this is 2. So multiplying everything by 2, so we have 2 times f cosine theta minus mg sine theta plus mv initial squared equals to mv final squared. Still, we can do something with this. We can divide everything by m on both sides, so we have v final by itself. We're going to go to the next board. So in the next board, we have v final squared happens to be, I'll just have to look back, 2 parentheses f cosine theta minus mg sine theta times d, and then plus mv initial squared all over m. That happens to be our v final squared. So v final equals to the square root of 2 f cosine theta minus mg sine theta times the displacement up the ramp plus mv initial squared all over m. So we're almost there. The next thing is to plug in the numbers as required. So we have 2. Our force happened to be 600 newtons, if you can recall. And then cosine of theta, theta happens to be 30 degrees, minus the mass of the professor is given us 85 kilograms. That's the professor and the chair. Okay, and by chair, we don't mean the chair of the department, but the chair they're sitting on, which is 85.0 kilograms, times sine of 30. Okay, remember we have a g right there, so we have to put g, don't forget the g, which is 9.8 meters per second. So times 9 oh, I gotta get this. Not doing it. Get that 9.8 meters per second squared, and then sine of times sine of 30 degrees multiplied by a distance of 2.8 meters. We have to add the mass again, 85.0 kilograms, times v initial, the initial velocity, if you can recall from the beginning of the problem, happens to be 2.00 meters per second. So this is 2.00 meters per second. We need to square that. Everything is divided by 85.0 kilograms. And we want to know what's the speed at the top. That's the v final. If you punch in the numbers, you see we have 600 there minus 85, 9.8, sine of 30, and then times, we have to get the displacement. The displacement happens to be 2 it's actually 2 she's pushed 2.5 meters. So we gotta clarify that. This displacement is 2.5, not 2.8. I don't know how we got 2.8 right there. So we have to come back and rectify that. The displacement happens to be this one. Okay, so we have to get 2.5 there, 2.5 meters. So 600 cosine 30, 85, 9.8 Okay, this is 9.8 meters per second times the displacement sine of d, m85. Plug in the numbers, we get 85 v final squares at 2.00 meters per second. So v final gives us a value of approximately 3.17 meters per second. So this is a strategy that you can use to find the final velocity. Keep the variable up until the end, and you get a lot of points for that. And you can always recheck your steps backward. So we had a professor that's being pushed up on incline, and the incline was at 30 degrees to the horizontal. The force being used is 600 newtons, and we have a bunch of kids that are pushing the professor up, distance of 2.5 meters at a initial speed of 2.00 meters per second. Thanks for watching. Hope you enjoyed the video. Feel free to send out questions, and looking forward to uh, posting more videos. So keep working on your problems, and we'll see you and have a wonderful day. Okay, thanks. Bye.